let's talk about one of the most beautiful and frankly powerful equations in all of science, the Dirac equation. And this thing is not just a bunch of math symbols on a page. No, it's a story. A story about a huge crisis in physics, a mind-bending stroke of genius, and a wild prediction that literally revealed a hidden half of our universe.
And look, to really get why this is such a huge deal, you have to understand that what Paul Dirac did is considered to be right up there with Newton's laws of motion or Einstein's relativity. I mean, we're talking about a true pillar of modern physics. So what was the problem he was trying to solve that put him in such legendary company?
Well, you gotta picture the scene. It's the 1920s, and physics is in the middle of a major identity crisis. It had these two spectacular theories that worked perfectly, but they were basically at war with each other.
And this conflict was deep. On one side, you had quantum mechanics, this amazing new theory that was just crushing it at describing the super weird world of atoms and electrons. And on the other side, you had Einstein's special relativity, which perfectly described things moving close to the speed of light. The problem? They were built on totally contradictory ideas about how space and time work. For physics to move forward, they needed one single theory that could handle both the incredibly small and the incredibly fast.
So naturally, the first thing everyone tried was, the obvious thing. Just take the famous Schrödinger equation and kinda smoosh it together with relativity. This gave him something called the Klein-Gordon equation. And for a minute, it looked pretty good, but it turned out to have this fatal flaw hiding inside it.
And here's where it all fell apart. The killer problem was this. The equation started spitting out answers that included negative probabilities. And that just makes no sense at all. It's like saying there's a negative 20% chance of rain. Probability has to be between 0 and 100, period. This wasn't some tiny rounding error. It was a giant red flag telling them their whole approach was fundamentally wrong. Physics was totally stuck.
And this is where Paul Dirac enters the story. He was this brilliant but famously quiet and reserved physicist who just saw the world differently. And the legend is that he had his big breakthrough while just staring into a fireplace, thinking about the mathematical beauty of it all.
Instead of trying to force things to fit, Dirac took a step back and asked a much more basic question. He saw that the Schrödinger equation treated time and space differently, mathematically. But relativity demands they be treated as equals. So he thought, you know what? Forget patching the old equation. What if we build a new one from scratch that's perfectly symmetrical, first order in both space and time, right from the get-go? His method was just pure genius. He basically looked at the main equation from relativity and tried to take its square root. Now, when he first tried it, he found it was impossible to do with just regular numbers. The math literally didn't work. But then he had this incredible leap of insight. It could work, you just couldn't use numbers. You had to use these special mathematical objects called 4x4 matrices. Now, this wasn't just some mathematical quirk, it had a massive physical consequence. It meant that the wave function you used to describe an electron couldn't just be one single number anymore. It had to be a list of 4 separate components. It created this whole new object that we now call a bispinor. And at the time, nobody really knew what all 4 of these parts meant, but the math insisted they had to be there. And this is where the story gets really cool. See, Dirac only set out to solve one problem, making quantum mechanics and relativity play nice. But his equation, it was so perfect that it started giving him answers to other huge puzzles in physics, almost for free.
He'd done it. He'd made a solid relativistic equation. But as he started playing with it, he realized it was telling him things about the electron he hadn't even asked for. It was describing more than he ever intended.
You see, for a while now, physicists knew that electrons acted like they were tiny, perpetually spinning tops. They called this property spin, but nobody knew why. In the old version of quantum theory, spin was just this extra thing they had to kind of staple onto the equations by hand to make them match their experiments. It was an awkward fix, just tacked on.
And then comes Dirac's equation. And unbelievably, it turns out that 2 of the 4 parts of his new wave function perfectly described the electron's spin, one for what we call spin up and one for spin down. Suddenly, spin wasn't an add-on anymore. It was a direct, unavoidable result of living in a universe that's both relativistic and quantum. The equation just predicted it, automatically.
But wait a minute. That only explains 2 of the 4 components. What about the other 2? Well, those pointed to something so bizarre, so completely unheard of, that at first, everyone thought it was the equation's biggest failure.
The other 2 solutions described electrons with negative energy. And that's
That's a terrifying idea in physics. It would mean a normal electron could just keep falling to lower and lower and lower energy states forever, spitting out an infinite amount of energy. It would mean that every single atom in the universe should be unstable and just collapse.
But Dirac, his mind just worked differently. He didn't see a flaw. He proposed something completely audacious. He said, what if the vacuum of space isn't actually empty? What if it's completely filled up with an infinite sea of these negative energy electrons? If all those states are already taken, then our normal, positive energy electrons have nowhere to fall. The universe is stable after all.
So let's follow this crazy logic. If this Dirac sea exists, what happens if a high-energy photon comes along and whacks one of those negative energy electrons so hard it pops out into our positive energy world? Well, you'd get a normal electron, sure, but you would also leave behind a hole in the sea. And that hole, that absence, would act just like a particle itself. It would have the exact same mass as an electron, but since it's a hole where a negative charge used to be, it would have a positive charge.
And that was the jaw-dropping conclusion. His equation wasn't broken. It was predicting a perfect mirror image of the electron, an anti-electron. This was the very first prediction of the existence of antimatter, an idea that didn't come from any experiment, but came purely from the beautiful, stubborn logic of an equation. I mean, what an absolutely wild prediction. A brand new particle identical to the electron in every way except for its charge, just dreamed up from pure math. The only thing left was to see if the universe actually played by Dirac's rules. And the proof, it came so fast it was almost dizzying. In 1932, just 4 years after Dirac published his paper, a physicist named Carl Anderson was looking at the tracks left by cosmic rays, and he found one. A track of a particle with the exact same mass as an electron, but it curved the wrong way in his magnetic field. It had to have a positive charge. He had found it. He discovered the anti-electron and named it the positron.
You really can't overstate how big of a moment this was. Think about it. For maybe the first time ever, a fundamental piece of our universe was found on paper, years before it was ever seen in an experiment. It was just this stunning proof that the abstract language of mathematics could uncover profound physical truths about reality.
And the equation's legacy today? It's just immense. It's the bedrock of quantum electrodynamics, which is our theory for how light and matter interact. It doesn't just describe electrons, it works for all the other fundamental matter particles, like quarks. It's a cornerstone of the standard model of particle physics. It's considered so important, it's actually inscribed on a plaque in Westminster Abbey, right there on the floor next to Isaac Newton. It is absolutely not an exaggeration to call it the real seed of modern physics. From one single, elegant equation, we got the explanation for quantum spin and the prediction of an entire new form of matter. Just incredible. And that leaves you with this profound and really tantalizing thought. The story of the Dirac equation is proof that sometimes the universe's biggest secrets aren't waiting for us in a giant telescope or a massive particle collider. Sometimes they're just waiting, hidden inside the beautiful logic of our equations, which makes you wonder, what else is in there, just waiting for us to find it?